Empty space holds the secret rivers that build galaxies. This video will give you a complete map of the invisible architecture guiding all cosmic growth. We will trace how stellar material travels across millions of light years, revealing the forces that decide where new stars are born and why others fade. You will discover why the universe is not a void but a vibrant network of flowing matter, and how these intergalactic pathways ultimately shape everything we see in the night sky. What do you believe shapes the destiny of a star? This cosmic web acts as the universe's ultimate superhighway, a sprawling network of invisible roads. Think of it less like a spider's web and more like the root system of a colossal, unseen tree, with tendrils reaching across the emptiness. These filaments are the true thoroughfares of the cosmos, and they are built upon a foundation we cannot see, dark matter. This mysterious substance forms a gravitational skeleton, an unseen framework that dictates where everything else, all the normal matter that makes up stars and planets, is allowed to flow. It is the architecture hidden behind the walls of space. Within the immense corridors of these filaments, which can span hundreds of millions of light years, rivers of superheated gas race silently. This gas is the primary fuel for the universe's continued growth, the raw hydrogen and helium that will one day coalesce into brilliant new galaxies and glittering star clusters. Where these filaments intersect, you find the great cities of the cosmos, dense clusters of galaxies thriving at the crossroads. The very shape and density of this web determines the destiny of cosmic material, guiding it toward these bustling hubs or leaving it adrift in the immense, quiet deserts of intergalactic space. So how does this raw fuel, this flowing river of gas, actually complete its journey into a newborn star? The answer lies in the specific conduits that act as cosmic pipelines, channeling this vital material directly into the hearts of waiting galaxies. A thin, luminous thread of gas, brighter than a million suns, connects two immense galaxy clusters. This is not a chance alignment but a cosmic pipeline in action, a filament channeling the raw material of creation. These glowing bridges are the primary conduits for the intergalactic medium, the vast reservoir of pristine hydrogen and helium that fills the voids between galaxies. They act as direct supply lines, funneling this vital fuel from the sparse cosmic deserts into the dense, bustling cities of galactic clusters. The process that makes this possible is known as cold flow accretion. It is a remarkably efficient delivery system where rivers of gas can stream along these filamentary pathways without being heated to extreme temperatures. This allows the gas to remain relatively cool and dense, flowing directly into the halos of waiting galaxies, ready to collapse and ignite into new stars. For a long time, this was a theoretical prediction, but observations from telescopes like Hubble have now captured the faint, ethereal glow of these bridges, confirming their role as the universe's essential supply routes. This discovery fundamentally challenges older models of galaxy growth, which suggested a much slower and more chaotic process. Instead, we see a highly organized and efficient network, a testament to the underlying architecture of the cosmic web. The sheer scale of this continuous accretion, this river of gas flowing on a million light-year journey, compels us to ask what powerful engines could possibly maintain such a relentless current through the emptiness of space. Gravity is the silent architect of these cosmic rivers, its influence far grander than a simple tug between stars. It carves the very channels through which the universe's raw material must flow. The primary source of this immense sculpting force is dark matter, the unseen substance that comprises the vast majority of all mass in the cosmos. This mysterious material forms an invisible scaffold, a deep gravitational landscape that guides everything we can see. Think of it as a network of sunken valleys etched across space, with every dip and trough dictating the path of the flowing gas. As entire galaxies and clusters sail through this dark matter terrain, they create immense wakes and currents, much like a ship moving through water. These gravitational disturbances act as cosmic signposts, funneling rivers of hydrogen and helium into specific, organized routes along the web's filaments. This is the essential guidance system that prevents stellar material from drifting into the eternal quiet of intergalactic space. Without this dark matter framework, the gas required to build new stars and galaxies would never coalesce so efficiently, leaving the universe a formless and disordered expanse. The invisible hand of gravity ensures that the fuel of creation is delivered precisely where it is needed most, directly to the bustling hubs of cosmic construction. Yet this journey is not always a smooth one, for what happens when these orderly rivers of gas finally reach their destination, only to meet the chaotic, violent environment of a living galaxy? A supernova's final act is one of immense creative destruction. When a massive star reaches the end of its life, it does not fade quietly. It erupts, hurling its own enriched substance, forged in its core and during the violent blast, far beyond the boundaries of its home galaxy. This is not a solitary event. Across the cosmos, supernova and the colossal winds from active supermassive black holes collectively generate titanic outflows. These forces act like galactic fountains, launching vast clouds of heavy elements, what astronomers call metals, high up into the galaxy's surrounding halo, a region known as the circumgalactic medium. This ejected material does not simply disappear into the void. Instead, it joins the grander flow of the cosmic web. The heavier elements, having been expelled with tremendous force, can be swept into the very same intergalactic pathways we have been exploring. There, this enriched gas can travel immense distances, eventually cooling and condensing. It might fall back onto its original galaxy in a great cosmic rain, or it could be captured by the gravity of a completely different galaxy, drawn into its own cycle of star formation. This is galactic recycling on the most epic scale imaginable. It means that the iron in your blood and the calcium in your bones were likely forged in the heart of a long-dead star, and then cast across space by such a fountain, eventually finding their way to a new stellar nursery and billions of years later to you. This cyclical motion of death feeding new life is fundamental to the evolving chemistry of the universe, but it raises a profound question about the very nature of this cosmic journey. How can we begin to track the flow of this invisible, recycled material as it travels through the darkness between the stars? A galaxy can be stripped of its very essence, its lifeblood torn away by an invisible tide. This is RAM pressure stripping, a cosmic interaction as dramatic as it is consequential. Picture a spiral galaxy, rich with clouds of cool gas, sailing at tremendous speed through the heart of a massive galaxy cluster. It is not moving through empty space, but through a sea of superheated, thin plasma known as the intracluster medium. The resistance from this scorching gas acts like a relentless cosmic wind, and for the galaxy, it is a hurricane. This wind exerts an immense pressure, so powerful that it can forcibly blow the galaxy's own star-forming gas right out of its gravitational grip. The galaxy's motion through the cluster becomes its own undoing, as the vital fuel for future stars is scoured away. We see the evidence in what astronomers call jellyfish galaxies, stunning objects that live up to their name. They trail long, glowing tendrils of gas that stretch for tens of thousands of light years, like cosmic tentacles being pulled from the galaxy's main body. This is not a slow leak but a violent harvest, where the galaxy's resources are being directly fed into the cluster's larger network. The star formation within that galaxy can be quenched almost entirely, leaving it a red and fading island. Yet, the story does not end with this loss. The stripped gas, once destined for a single galaxy, now joins the broader flow. It enriches the intracluster medium itself, becoming part of a vast, communal reservoir of material that may eventually seed new generations of stars elsewhere in the cluster. This dramatic process forces us to look beyond individual galaxies and ask where all this flowing, cycling, and harvested material ultimately gathers. What are the final destinations for the universe's stellar building blocks? Galaxy clusters are the universe's grand central stations, where the great cosmic highways finally converge. Here, at these immense crossroads, the silent flow of intergalactic material reaches its ultimate destination. The sheer gravitational might of a cluster, dominated by its vast halo of dark matter, acts as a powerful cosmic siphon. It pulls in rivers of gas from the surrounding filaments over billions of years, gathering the fuel that has traveled across the void. All this accumulated matter collects in a seething, luminous sea known as the intracluster medium. This is not empty space. It is a superheated plasma, a thin but incredibly energetic gas that fills the entire cluster, glowing in X-rays and enriched with the heavy elements from countless galactic fountains and violent mergers. This vast reservoir is the final repository for so much of the stellar material we have followed, yet it is far from a quiet graveyard. The dynamics within this plasma are what ultimately decide the fate of galactic construction. In the dense hearts of some clusters, this superhot gas can gradually lose energy and cool. As it cools, it becomes denser, and under the immense pull of gravity, it can flow back into individual galaxies, providing a fresh supply of fuel for new rounds of star birth. This is the cosmic cycle completing itself, with the cluster acting as both a terminus and a redistribution center. But this process can be violently interrupted. When entire galaxy clusters collide in the most energetic events since the Big Bang, the resulting shock waves rip through the intracluster medium. This reheats the cooling gas to even more extreme temperatures, temporarily shutting down star formation and stirring the cosmic pot, redistributing matter and energy on an unimaginable scale. The life cycle of a star, therefore, depends on the delicate and violent thermodynamic balance within these colossal hubs. It forces us to wonder if the gas can cool and reignite. What are the specific conditions that allow for this final, crucial step in the journey from an invisible filament to a brilliant, newborn sun? Deep within a galaxy cluster's core, a paradoxical battle unfolds that defies simple expectations. A vast ocean of superheated gas should naturally cool down. As this gas radiates away its tremendous energy, it grows denser and should begin a steady, inward rain, a phenomenon astronomers call a cooling flow. This river of condensing gas should pour onto the cluster's central galaxy, triggering an explosive burst of new stars, a stellar fireworks show that would light up the cosmos. Yet, for many of the universe's most massive galaxies, this torrent of cold fuel never arrives. The predicted deluge of star birth is conspicuously absent, leaving astronomers with a profound mystery. Where does all that potential go? The answer lies in a cosmic thermostat, a self-regulating loop of feedback that prevents the system from running out of control. The primary source of this regulation is often a supermassive black hole at the galaxy's heart. When gas begins to flow inward, some of it feeds this dormant giant, awakening it as an active galactic nucleus. The black hole does not consume quietly. It erupts, launching jets of intensely energetic particles and generating powerful shock waves that ripple back through the surrounding gas. This is not a gentle warmth but a blast furnace, reheating the cooling reservoir and halting the inward flow. The gas is stirred back up to immense temperatures, and the star-forming rain is shut off. This creates a remarkable cycle, a balancing act between the natural tendency to cool and the violent intervention that provides heat. It is a feedback loop that governs the very pace of cosmic construction, ensuring that the largest galaxies do not burn through their fuel supply in a single frantic burst. This delicate equilibrium connects the fate of a single galaxy to the grand architecture of the cosmic web itself. For the efficiency of this entire process depends on the environment the galaxy calls home. A galaxy's address within the cosmos is the single greatest predictor of its future. Two galaxies, born as twins with the same mass and the same brilliant blue glow of young stars, can embark on entirely different life paths based solely on their location. One drifts into the dense, bustling core of a galaxy cluster, while its sibling remains in the quiet, sprawling suburbs of a cosmic filament. Their destinies are no longer their own. For the galaxy entering the cluster, It is a descent into a hostile environment. It faces a constant barrage of gravitational nudges from close encounters, which can warp its elegant spiral structure. More critically, it plunges into that sea of superheated plasma, the intracluster medium, where the relentless ram pressure wind begins to strip away its star-forming gas. Simultaneously, the galaxy can be strangled, a slower but equally fatal process where its extended reservoir of fresh gas is torn away, cutting off the supply of new fuel. The result is a galaxy quenched, its star formation snuffed out, leaving it to slowly redden and fade. Meanwhile, its isolated twin continues its peaceful existence. Safely embedded within a filament, it maintains its connection to the cosmic web's supply lines. A steady, cool flow of pristine gas from the intergalactic medium continues to feed its star-forming factories, allowing it to retain its vibrant blue hue and sustain its creative output for billions of years longer. This profound environmental dependency reveals that a galaxy's morphology, its color, and its very lifespan are not merely internal affairs. They are a direct reflection of its access to the cosmic highways, a testament to whether it resides at a busy, violent intersection or a quiet, nourishing stretch of road. To truly understand any single galaxy, we must first read the map of the entire cosmic web it calls home, a structure that is itself not static, but evolving over the deepest of time. We can map the subtle currents that guide entire galaxies through the void. This is the large-scale velocity field, a dynamic chart of cosmic movement. It reveals not just where galaxies are, but where they are flowing, pulled by the immense gravitational tides generated by the largest structures in the universe, like superclusters and mysterious great attractors. Picture a river flowing toward a waterfall. The galaxies and the gas between them are like leaves on that river's surface, carried along by a current they cannot resist. These are not random motions but coherent streams, where entire groups of galaxies move together in a vast, silent migration toward regions of overwhelming density. By meticulously measuring the velocities of thousands of galaxies, astronomers can trace these flows backward. They can reconstruct the invisible pathways along which intergalactic gas is being channeled, revealing the preferred routes for stellar material on its billion-year journey. This transforms our view of the cosmos from a static map of lights into a living, fluid universe in motion. Galaxies become natural tracers, their movements illuminating the contours of the underlying dark matter landscape that guides everything. Observing these cosmic currents provides some of our strongest, albeit indirect, evidence for the hidden architecture of the cosmic web. So how do we actually measure the silent, stately flow of an entire galaxy across the expanse of space? The most powerful flashlights in the universe are not built by human hands. They are quasars, the brilliant hearts of distant galaxies, powered by insatiable supermassive black holes. Their light, traveling for billions of years to reach our telescopes, does not make the journey unimpeded. It passes through the very fabric of the cosmic web, the vast, diffuse clouds of the intergalactic medium. And just as a prism splits sunlight into a rainbow, a spectrograph breaks this ancient quas, our light into its constituent colors, revealing a story written in absence. What astronomers find is a forest, not of trees but of lines, a dense, intricate pattern of dark stripes cutting across the spectrum, each one a tiny bite of light stolen by a specific atom within a specific cloud of intergalactic gas. This is the Lyman Alpha Forest, and it is our most direct window into the invisible rivers of the cosmos. Each absorption line is a data point. Its position tells us the distance to that particular cloud of hydrogen. Its width reveals the cloud's temperature and motion. And if the line corresponds to a heavier element, like carbon or oxygen, it signals that this primordial gas has been enriched by the ashes of long-dead stars. By reading this forest line by line, astronomers can reconstruct a core sample of the cosmic web along that single, piercing line of sight. They can measure the density of the gas filaments, trace their flows, and even uncover the history of galactic pollution across cosmic time. This is how we transform an invisible highway into a detailed, three-dimensional map. It proves that the emptiness of space is an illusion, a canvas teeming with structure we are only just learning to read. Our cosmic census of the universe revealed a startling shortfall. For decades, astronomers tallied all the normal matter they could see, the stars, galaxies, and gas clouds, and found it accounted for only about half of what the Big Bang's recipe predicted should exist. An enormous amount of the universe's ordinary building blocks, the baryons that make up everything from planets to people, was simply missing. The question haunted cosmology. Where had half the universe's tangible substance gone? The answer was hiding in plain sight, woven into the very fabric of the cosmic web. The missing matter had not vanished. It was simply too faint to see, existing as a diffuse, superheated plasma known as the Warm Hot Intergalactic Medium, or the WHIM. This is not a cold, dense gas but a seething ocean of million-degree hydrogen and helium, so thin that a single coffee mug full of it would contain just a few atoms. At this extreme temperature, it emits almost no visible light, rendering it nearly invisible to our traditional telescopes. So how do you find a ghost? You watch for its shadow. Astronomers detect the WHIM by observing how it subtly affects the light from even more distant objects. As the light from brilliant quasars travels through these filaments of hot gas, the WHIM absorbs specific, high-energy wavelengths in the ultraviolet and X-ray parts of the spectrum. It also leaves a faint imprint on the cosmic microwave background, the afterglow of the Big Bang itself. These tiny, telltale signatures confirm a profound truth. The great voids between galaxies are not truly empty. They are saturated with this vast, hot ocean, a reservoir that finally accounts for the universe's missing mass. This discovery fundamentally completes our inventory of the cosmos, placing the final pieces of ordinary matter precisely where the cosmic web's architecture predicted they should be. But finding this hidden sea of plasma forces a new and deeper question. What are the physical properties of this pervasive medium, and how does its intense heat influence the delicate process of star formation in the galaxies it surrounds? This searing cosmic ocean is the final resting place for half the universe's ordinary matter. The warm, hot intergalactic medium is a plasma of staggering scale, with temperatures soaring between 100,000 and 10 million degrees. It is not a uniform fog but a structured sea, its vast currents and dense knots meticulously tracing the invisible architecture of the dark matter web. This gas is heated to such ferocious extremes by immense shocks, generated as it plummets into the gravitational valleys of cosmic filaments, and by the continuous energy input from galactic fountains and active black holes. To find this pervasive ocean, astronomers must look not for its faint glow, but for the ghostly fingerprints it leaves on light passing through it. Using sophisticated X-ray and ultraviolet telescopes, they search for the unique absorption signatures of highly ionized atoms, like oxygen and neon, atoms that have been stripped of most of their electrons by the incredible heat. Each detected line is a coordinate in this invisible map, confirming that the great voids are saturated with this tenuous, yet overwhelmingly dominant, phase of all normal matter. Its discovery completes our cosmic inventory, but it also introduces a profound thermodynamic puzzle. This is the raw fuel for all future stars, yet it is trapped in a state of intense, seething agitation. So how does this scorching plasma, the primary substance of the cosmos, ever manage to cool down enough to collapse into the cold, dense cradles of new suns? These silent cosmic currents are far too slow for any single observer to witness. So how can we possibly test our understanding of these billion-year journeys? We build our own universes inside supercomputers. Cosmological simulations are digital laboratories where we recreate the entire evolution of the cosmos, from its primordial beginnings to the intricate web we see today. Projects like IllustrisTNG and Eagle are not simple animations. They are vast, mathematical universes governed by the fundamental laws of physics. Gravity pulls virtual dark matter into its cosmic scaffold. The dynamics of fluids model how gas flows and shocks. The physics of star formation and the explosive feedback from supernova and black holes are all programmed in. We set the initial conditions, press play, and then watch as a virtual universe unfolds over billions of years of simulated time. We can witness the birth of the first filaments, see galaxies begin to sparkle at their intersections, and track the flow of individual packets of gas as they travel from the void into a galactic disk, and then are perhaps blown out again by a stellar wind. This virtual experimentation is invaluable. It allows us to run tests we could never perform in reality. What happens to a galaxy if we turn off supernova feedback? The simulation shows us it would form stars in an uncontrolled frenzy, quickly exhausting its fuel. How does gas from the cosmic web actually penetrate a galaxy's halo? The simulation reveals delicate streams of cold gas slipping through the hot surrounding medium. These digital realms help us interpret the snapshots we get from our telescopes, transforming a single, static observation into a dynamic moment in a much grander story. They are the proving grounds for our theories about the cosmic flow, predicting subtle phenomena that we can then actively search for in the real night sky, forever blurring the line between the universe we observe and the universes we create. The oldest light in the universe carries the ghostly imprint of everything it has passed. We can see the shadow of a galaxy cluster cast upon the cosmic microwave background, the afterglow of the Big Bang itself. This phenomenon is known as the Sunyaev-Zeldovich Effect. It works like this. Photons from that primordial light, traveling for nearly 14 billion years, encounter a massive galaxy cluster filled with a sea of superheated electrons. As these ancient photons collide with the fiercely energetic electrons, they receive a tiny boost of energy, a process called inverse Compton scattering. The result is a subtle but measurable distortion in the background light spectrum. At certain radio frequencies, this shows up as a distinct cold spot, a shadow on the sky. The deeper the shadow, the greater the electron pressure within that cluster's gas. This gives astronomers a direct way to measure the density and temperature of the hot plasma trapped in these cosmic hubs. The true power of this technique lies in its independence from distance. Unlike methods that rely on a structure's brightness, which fades with redshift, the Sunyaev-Zeldovich effect is just as clear for a faraway cluster as for a nearby one. This allows us to construct vast, unbiased maps of the large-scale structure, revealing the distribution of hot gas along the filaments of the cosmic web itself. We are essentially reading the pressure of the universe's hidden oceans, using the most ancient light as our backlight. This provides a crucial, complementary view to other observations, revealing the immense thermal energy stored within the scaffolding of the cosmos. Energy that governs whether gas can cool and collapse or must remain in a seething, starless state. Yet another invisible hand guides these cosmic rivers. Woven through the vast emptiness between the galaxies and along the filaments are magnetic fields. These are not the powerful magnets we know, but incredibly faint traces of force, 1,000,000 times weaker than the field that protects our own planet. Their origins are ancient, likely stretching back to the universe's earliest moments, and they have been stretched and amplified by the turbulent winds from galaxies and their central black holes. Once seeded into the intergalactic void, these subtle fields act as cosmic guide wires. For the searing plasma of the warm, hot intergalactic medium, which is made of charged particles, these magnetic lines can gently channel the flow, adding a layer of direction to the grand pull of gravity. They provide a faint pressure, a form of invisible structure that can help support a cloud of gas against its own weight, potentially slowing its collapse into new stars. This magnetic influence even extends to the journey of cosmic rays, those high-energy particles racing across the universe, and it can change the very viscosity of the intergalactic plasma, altering how shock waves travel and energy dissipates along the cosmic web. Proving their existence is a monumental task, as detecting such a weak signal across millions of light years pushes our instruments to their absolute limits. But their theoretical presence reminds us that gravity is not the only sculptor. The journey of stellar material is not just a fall into gravitational valleys, but a guided voyage along these invisible magnetic rails, adding a crucial, non-gravitational force to the equation of cosmic evolution. The serene rivers of the cosmic web are actually raging torrents. This turbulence is a fundamental feature of the intergalactic medium, a chaotic energy generated by the most violent events in the universe. When galaxies collide in titanic mergers, when supermassive black holes blast out jets of plasma, and when supernova drive galactic winds, they do not just push gas. They stir it, injecting immense energy that ripples across millions of light years. This is not a gentle stirring, but a violent churning that transforms the smooth flow of gas into a complex, frothing soup. This chaos plays a surprisingly constructive dual role. On one hand, turbulence acts as a great cosmic mixer. It churns and blends different phases of gas, ensuring that the heavy elements forged in stellar furnaces are distributed far more uniformly than gravity alone could manage. This widespread enrichment seeds the entire circumgalactic medium with the potential for rocky planets and, ultimately, life. Yet turbulence also acts as a form of support. The constant, churning motion provides additional pressure that can prop up vast clouds of gas, effectively holding them aloft and slowing their gravitational collapse into new stars. It is a cosmic balancing act between chaos and creation. To accurately model how a galaxy forms stars, we must therefore understand the nature of this intergalactic turbulence, its intensity, and how its energy ultimately dissipates back into the quiet background of space. This small-scale physics, operating within the grand channels of the cosmic web, ultimately dictates the efficiency with which the universe's raw material can cool, condense, and finally ignite. The universe's great rivers are not made of water, but of matter in three distinct states. Intergalactic gas can be cold and neutral, warm and ionized, or exist as the scorching plasma of the warm-hot intergalactic medium. These are not separate bodies of water, but different currents within the same cosmic flow, often existing side by side in a delicate balance of pressure. A single filament can contain all three, a layered structure where the fate of the material hinges on its temperature and density. This multi-phase nature is the universe's primary mechanism for regulating its own growth. The constant transition between these states acts as a cosmic throttle, controlling how quickly raw material can be converted into new suns. When a pristine stream of cold gas, flowing peacefully along a filament, suddenly slams into the crowded environment of a galaxy cluster, it experiences a violent shock. This is the equivalent of a river hitting a sheer cliff, instantly transforming the calm, cold flow into a turbulent, hot waterfall of plasma. The gas is shock-heated, its atoms stripped bare, and it joins the seething intracluster medium. Its journey toward becoming a star is abruptly put on hold, but the cycle can also run in reverse. In the dense, tangled knots where filaments intersect, or within the vast, quiet halos surrounding galaxies, pockets of the hot WHIM can gradually lose their immense thermal energy. Over millions of years, this gas radiates its heat away, cooling and condensing. It transitions first into the warm phase and then, if conditions are right, further condenses into the cold, dense clouds that are the true nurseries for stellar birth. The entire cosmic ecosystem depends on this dynamic equilibrium between heating and cooling. If the hot phase dominates, star formation is stifled. If the cold phase can accumulate, galaxies blaze with new light. This continuous cycle of phase transitions is the essential heartbeat of a living cosmos, the silent process that determines whether a river of gas remains a barren, hot stream or condenses into a rain of new suns. A galaxy's grand design, its sweeping spiral arms or its smooth elliptical haze, is written by the rivers that feed it. The very form a galaxy takes, whether a spinning pinwheel of star birth or a quiet sphere of aging suns, is a direct consequence of how it gathers its raw material from the cosmic web. Picture a spiral galaxy like our own Milky Way, Its majestic structure depends on a delicate, continuous supply of cold gas, a gentle rain that flows steadily along a filamentary pathway. This smooth, ordered accretion delivers gas with a high degree of angular momentum, causing it to settle into a vast, rotating disk. Within this disk, density waves create the iconic spiral arms, compressing the incoming gas and triggering the brilliant blue glow of new stars. The galaxy becomes a self-perpetuating engine of creation, its form maintained by the quiet, consistent nourishment from its cosmic supply line. This is the destiny of a galaxy living in a peaceful suburban stretch of the web. But what happens when the delivery is not a gentle stream, but a violent downpour? When galaxies collide in a major merger, the resulting chaos is a galactic demolition derby. Their delicate disks are shredded, their gravitational fields intertwined. Vast amounts of gas are violently funneled directly toward the newly merged galactic core, fueling a ferocious burst of star formation and feeding the central supermassive black hole. In this turbulent process, the ordered rotation of the original spirals is completely scrambled. The angular momentum of the gas is lost, and the final product is no longer a spinning disk, but a smooth, rounded, and largely featureless elliptical galaxy. The starburst frenzy quickly consumes the remaining gas, leaving behind a population of old, red stars with no new fuel to create bright blue spirals. The galaxy's morphology, therefore, is a fossil record of its accretion history. A steady diet of cold flow builds and sustains a spiral. A single, chaotic feast from a merger can transform it into an elliptical. This reveals that the intergalactic pathways are far more than simple fuel lines. They are the master sculptors, their rhythm and mode of delivery chiseling the vast and beautiful diversity of the galactic forms we see scattered across the night. The ancient light from a quasar, 13 billion years old, holds a secret. Its spectrum is etched with a dense, intricate forest of absorption lines, more crowded than in any modern equivalent. This is our clearest window into the cosmic web of the infant universe, a time when the entire cosmos was a denser, more compact place. The intergalactic medium back then was not the searing, ionized plasma we see today, but a cooler, more neutral fog of primordial hydrogen and helium. Within this fog, the gravitational pull of dark matter had already woven the first filaments, and along these pathways, rivers of pristine gas flowed with an efficiency never again matched. This was the era of cold flow accretion in its purest form. Galaxies, themselves in their infancy, were not yet surrounded by massive, hot halos that could disrupt incoming streams. Instead, these cold rivers of fuel could flow directly and unimpeded into the hearts of the first protogalaxies. This constant, rapid influx of raw material powered incredible bursts of star formation, lighting up the early darkness. It also fed the voracious appetites of the first supermassive black holes, allowing them to grow to colossal sizes in a surprisingly short time. By studying these high redshift beacons, we see the cosmic web not as a mature, balanced system, but in its most dynamically active phase. It was a universe of rapid construction, where the foundational pathways were establishing the very rules of galactic growth. This pristine environment acts as a perfect laboratory, allowing us to observe the fundamental physics of gas accretion without the later complications of galactic pollution and violent feedback. How did these first structures, born from such simple, efficient flows, eventually grow complex enough to forge the elements for planets and life itself? The universe's great rivers are destined to run dry. As dark energy relentlessly stretches the fabric of space, the grand architecture of the cosmic web will slowly be pulled apart. The filaments that now channel rivers of gas between galaxies will become more tenuous, their gravitational pull weakening over billions of years. The steady flow of fresh hydrogen and helium from the intergalactic medium will gradually slow to a trickle, and then, for all practical purposes, it will stop. Galaxies will find themselves increasingly isolated, their lifelines to the cosmic supply network severed one by one. They will enter a state of cosmic drought, forced to rely solely on their internal reservoirs of gas. For a time, star formation can continue, burning through this remaining fuel. But with no new material arriving from the vast external reserves, this is a finite resource. The brilliant blue glow of young star clusters will become rarer, flickering out as the last pockets of cold, dense gas are exhausted. The universe, now dominated by dark energy's repulsive force, will grow quieter and darker. The vibrant, interconnected metropolis of galaxies we see today will slowly fragment into isolated islands, each one growing more quiescent as its stellar population ages and reddens. This long-term projection, born from our understanding of the current intergalactic flows, connects the dynamic cosmos we inhabit to a future of profound stillness. It suggests a finality to the great cycle of stellar birth and death, a quiet closing chapter written by the same forces that once guided the construction of everything we see. Our next great leap in mapping the cosmic web is already underway. Powered by a new generation of astronomical observatories, the James Webb Space Telescope acts as a time machine, its infrared gaze piercing the haze of the early universe to witness the very first galaxies as they tap into their primordial fuel lines. It captures the moment cold streams of gas first began feeding infant stellar systems, revealing the initial conditions of cosmic structure itself. Meanwhile, the upcoming Athena Observatory will turn its X-ray vision toward the faint, searing heat of the Warm Hot Intergalactic Medium. This mission is designed to do more than just confirm the WHIM existence. It will chart its density and temperature with exquisite detail, transforming ghostly theoretical filaments into a precise, three-dimensional map of the universe's hidden ocean. On the ground, colossal instruments like the extremely large telescope will employ advanced adaptive optics to cancel out the blurring effect of our own atmosphere. This allows for incredibly sharp views of the circumgalactic medium, the chaotic zone where galactic fountains erupt and incoming filaments of gas are captured. We will watch in real time how galaxies interact with their cosmic supply lines, absorbing some material and expelling others. Together, these new eyes on the sky will do more than just fill in the blanks on our existing maps. They are poised to discover entirely new phases of intergalactic matter and witness dynamical processes we have only ever simulated inside supercomputers. The next decade of observation will not merely add detail. It will rewrite the story of how the universe channels its raw material, moving us from a schematic diagram to a living, breathing movie of cosmic evolution. Even with our most advanced maps, the cosmic web holds its deepest secrets close. We have traced the rivers of gas and charted the invisible architecture, yet fundamental puzzles about their nature remain unsolved. The efficiency of cold stream accretion, for instance, is a major unknown. Just how much pristine gas can these delicate filaments actually deliver to a hungry galaxy? Our simulations suggest it should be a primary fuel source, but directly measuring this faint, cool flow against the brilliant background of stars and hot gas is a monumental observational challenge. We are still learning the rules of this cosmic delivery system. Then there is the mystery of magnetic fields on a grand scale. How did these faint, ghostly forces, a million times weaker than Earth's own magnetic field, first come to be woven through the vast voids between galaxies? Were they born in the universe's earliest moments, or were they forged later by the violent winds from quasars and supernova? Their origin story is still being written, and understanding it is crucial, as these fields may gently guide the flow of charged plasma along the web's filaments. The detailed physics of galactic winds presents another frontier. When a supernova blast or a black hole's jet hurls material out of a galaxy, how exactly does this turbulent energy dissipate into the calm of the intergalactic medium? Does it simply heat the surrounding gas, or does it also trigger the condensation of new clouds, potentially seeding star formation in unexpected places? This complex feedback loop, the precise balance between the gas flowing in and the material blowing out, is the very heartbeat of galactic growth. Getting the math right on this cosmic equation is what separates a thriving spiral galaxy from a quiescent red one. Each of these open questions is a compass point for the next generation of explorers. They remind us that every new discovery does not simply fill a blank space on the map. It often reveals an entirely new dimension of complexity in the journey of stellar material, ensuring that the exploration of the cosmic web will continue to unveil wonders for generations to come. We create digital universes only to look back at them through a synthetic telescope. This is the power of synthetic observations, a technique that builds a direct bridge between our theoretical models and the reality we observe. Scientists take the raw output of a cosmological simulation, a universe of millions of data points representing gas density, temperature, and velocity, and they process it through a virtual instrument. They add the precise noise, the resolution limits, and the spectral distortions that a real telescope like Hubble or James Webb would encounter. The result is not just a beautiful animation, but a perfect, artificial dataset that looks exactly like a real observation. It is a universe as it would appear to our eyes and our instruments. This allows for a true apples-to-apples comparison. Does the intricate web of gas filaments in the simulation produce the same subtle absorption features in a quasar's spectrum as we detect in reality? Does the distribution of hot gas in a simulated galaxy cluster create the same X-ray glow and the same shadow on the cosmic microwave background that our telescopes measure? When the synthetic observation matches the real data, it is a profound validation that the physics baked into the simulation, from gravity to gas dynamics to feedback, is correct. But when there is a mismatch, it is not a failure. It is a discovery. It points directly to a missing ingredient in our understanding, perhaps an overlooked source of heating, a miscalculation in how gas cools, or a subtle magnetic effect we have not yet accounted for. This iterative dialogue between the simulated and the observed is how we refine our map of the cosmic web, turning speculative lines into confident, validated pathways. It proves that our most advanced theories are not just abstract mathematics, but accurate reflections of a structured and flowing reality. Our journey reveals a cosmos fundamentally woven together by invisible rivers. The silent movement of stellar material across the Great Dark is not a side effect of the universe, but its central creative engine. This continuous flow builds the majestic architectures of galaxies, fuels the brilliant fires of newborn stars, and seeds the void with the very elements that make planets and life possible. We have traced this grand cycle from its origins in the gravitational pull of unseen dark matter, through the scorching plasma of the cosmic web, to the dynamic feedback loops that regulate galactic growth. This is not a static void but a living, breathing system of immense complexity and beauty. As our tools evolve, from next-generation telescopes to ever more powerful simulations, our map of these celestial highways will transform from a rough sketch into a high-definition film of cosmic evolution. The next time you gaze at the night sky, remember that the quiet darkness between the stars is not empty. It is a vibrant network of flow and connection, a cosmic circulation system that has shaped every glittering point of light you see. We would love to hear what part of this journey through the cosmic web surprised you most. Share your thoughts in the comments, and subscribe for more explorations into the deepest mysteries of space.